Recording. You're able to hear me, right?
Yes, ma'am.
Okay. Let me also share my screen. You are able to see my screen, right?
Yes, ma'am. Yes.
Okay. Yeah. I welcome you all for the week 6 live interactive session for the course Polymers, Concepts, Properties, Uses, and Sustainability. Okay. Now let's get on to the session. So, as usual, we'll have a brief recap of lectures of week 6. So, week 6 lectures were all based on properties of polymers. Okay. So the first lecture was on physical and chemical aging. This was based on sustainability aspect. So first of all, aging in polymers was introduced. So aging can be due to different effects. It can be due to presence of oxygen or moisture, or it may be due to heat, or due to pH or some thermal effects. So and what happens in case of a physical aging and then a chemical aging, where in case of a chemical aging you will have chain scissions and all happening, right? Chain scission or even cross linking can happen. In case of physical aging, you will see some orientation changes and all. Okay. And then examples of aging was discussed. Here, the degradation of polyisoprene was discussed. And then the next was on aging in wood, which is a natural polymer, right? So, what happens in case of an aerobic aging and what happens in case of anaerobic. So, aerobic means in the presence of oxygen or air, right? Anaerobic is absence of oxygen. And then how the destruction happens. So, the destruction, especially the microbial based destruction, is what is which is demarcating the natural polymers from the synthetic polymers. And this is where people are working to add certain groups so that these kind of microorganism based degradation can happen, so that the sustainability aspect is introduced into the synthetic polymers, right? How identification of groups using FTIR happens. So in functional groups can be identified using this FTIR technique. So any functional group changes that happens due to aging or certain effects, then you can identify, for example, initially how it is, what are the functional group present initially, and over the time what was the change in the functional group. That gives an idea that certain effect has certain stimulus has caused this kind of an effect in the material, right? And what happens with the property changes with aging. So there was a discussion on compliance changes with aging, right? And the concept of accelerated testing. This is very important in terms of lifetime predictions. So, for predicting the lifetime of a material, for example, if you are going to give a 25 years of life for the service life for the material, you cannot do the study for all 25 years. You don't have all that time. For example, if it is going to work in some, it has to work in some acidic condition of pH 3, means you cannot give for 25 years, means you cannot do the testing for 25 years. But how you do and estimate that it can survive for 25 years is that you do it under much more stringent conditions. For example, instead of pH 3, you do it at pH 10 for a shorter duration of time. And then you can develop correlations so that you can give. So for pH 1, it has withstood the pH for this much of time. So if it is pH 3, this then it can withstand this much of time. You can create correlation, and then you can predict the life of the material. Okay, this is how the accelerated testing is done. Whether it is, if it is temperature, means much more stringent temperature. Either if it is you're going to use a material under very cold condition, then the testing is done under extremely low temperatures. Or if it is going to be used in very high temperature conditions, then testing is done at much higher temperature, and then you are estimating the life of the material. Okay, you're able to recollect.
Yes, ma'am.
Okay.
Yes.
Yeah. So the next lecture was on solution properties. Okay. So here the concept of overlap concentration. So what is a dilute polymer solution, and then what is the overlap concentration, and when it becomes semi-dilute. So in case of overlap concentration, the polymer molecules just starts touching each other. Okay. So the property starts varying once it crosses that overlap concentration and gets into the semi-dilute regime, because in dilute regime it is more of solvent and polymer interaction. But the concentration starts increasing and goes beyond the overlap concentration, there will be much role of a polymer-polymer interaction as well. And then the concept of intrinsic viscosity was introduced, and then Markovin's equation was discussed. The next was on there was a discussion on theta temperature. So where the polymer in polymer in the solvent, it behaves as a ideal chain. That is the that temperature is the theta temperature, and it varies from polymer to polymer, and also it varies from polymer solvent combination. For example, for particular polymer, if there are three different solvents, and each of the solvent will have different theta temperature as well. And then the solubility parameter was also discussed. And then the macromolecular solvent interaction was discussed, and how the macromolecular size, uh, it plays the role. And how can you determine the size of the macromolecule based on the solvent and polymer interaction using a light scattering, or using a GPC technique was all discussed. Next was the concept of the orientation or persistent length. Right. So persistent length is nothing but how far you have the correlation, persistence of correlation between one segment of the polymer and a segment which is far away. Okay. And finally the persistence chain was discussed. Right. uh, the next lecture was on conducting polymers. So first of all, electrical conductivity and ionic conductivity, these terminologies, basic terminologies, the charge was, the concept of charge, and uh, the number of charge units were all discussed. And then conducting polymer, where electronic conduction, in polymers, how it happens, there requires a certain amount of doping is also needed. And what are the different conducting polymers? One of the primary requirement of a polymer to be conducting is a delocalized electron, especially the electronic conduction, delocalized electron. So there is also another aspect called ionic conduction, right? Where there can be groups that can dissociate even in polymers. Like for example, you may have some groups like COOH group which can dissociate into COO minus and H plus. But here the discussion was primarily on the electronic conduction, where the conjugated delocalized electron was primary importance. And then all polymer device was discussed. Okay. Here a field effect transistor and a electrochromic display, where every component was a polymer, right from the substrate, to a conducting polymer was used, a dielectric polymer was used to make on all polymer, electronic device. And then application was discussed. The next lecture was on dielectric response or dielectric properties. You're able to hear me, right?
Yes, ma'am. Yes.
Okay. And you're able to follow, right?
Yes, I am able to recall.
Okay, good, good. So, in dielectric response, first of all, the type of responses. Initially, the linear response and the non-linear response. The basic concepts of a linear and non-linear response was discussed. Okay. So for example, in case of a there is in case of a linear response, there is a linear correlation, whether it can be algebraic or an ordinary differential equation correlation. And then the perturbation is very small. Okay. And then there is some displacement of the molecules only. There is no significant changes in the structure or orientation of the system, and it is just perturbed from one equilibrium state to the another. So these are the aspects of linear response. And then what are the aspects of non-linear response was discussed. And then what are the complexities in response of polymers? So was discussed in detail, especially the concept of energy storage and loss. Okay, whether it is mechanical energy storage and loss, or electrical energy storage and loss. So these concepts were all they were given an introduction in this lecture. The next lecture was again on dielectric response of polymers. So here there was a detailed discussion on the dielectric spectroscopy, dipole in polymers, polarization in polymers, the orientational polarization, and then there was a detailed discussion on the debye relaxation. Okay, the debye model was discussed, and there was a discussion on the debye relaxation. Okay, uh, the lecture 43 was on plasticity. So the concept of yielding was, uh, you know, uh, was introduced. What is, yield stress and yield strain, and then the strain softening, strain hardening, and then models for and what causes plasticity in polymers, right? So these were discussed, and then two models, basic models. One was Eyring model, and then the other one was the Ramberg Osgood model. So these two models were discussed. Lecture 44 was on properties of composites, right? So what are the shape, size, and different types of fillers, and uh, how do you actually pre-mix the fillers for easier processing. Though as a fiber size and all, we saw in one of the previous lectures that the ease of processing decreases with the length of the fiber, that is being reinforced, right? So but how best the processing can be made, so the like formation of a pre-preg, so these were all introduced. And then the composite properties is a function of constant properties, so parallel and series mixing rule and Halpin-Tsai model was discussed. And then how does the composite amount, not only the amount but its distribution and orientation also plays an important role in the properties and the processing of polymers. And finally, or electrical conductivity of composites was discussed, especially for the dilute systems. The Maxwell model was discussed. So these were all the uh, lectures, topics that were discussed in the week 6. Now let's get on to the practice assignment sessions. Hope you were able to just recollect, right?
Ma'am, I have a doubt.
Yeah.
Is the persistent length and contour length same for a
Uh,
polymer?
no, persistent length and contour length. Contour length is that when you stretch the polymer, the entire end to end, once you stretch the polymer, the entire end to end distance is your contour length. And then persistent length, it actually determines how the correlation is. It actually says how rigid is the polymer. Okay. The rigidity of the segments and all, is what is decided by the persistence length. You're able to remember something?
No, ma'am.
In fact, there was a discussion in the during the persistence length discussion, where your mean square end to end distance uh, was correlated to the persistence length and contour length, and at which point it becomes equal to contour length. It becomes directly proportional to contour length, and at what point it becomes square root of contour length was discussed. Maybe I'll just open the lecture. Just give me a minute so that second. You're able to see my screen, right?
Yes, ma'am.
Yeah. So your persistent length actually decides the bending stiffness, okay, of the polymer, and this is what I was talking about. The correlation between your end-to-end vector and your persistent length and the contour length, right? So for very small values of persistent sorry, for a very large value of persistent length, then this becomes, your this term, the exponential term here, it goes to uh, the denominator goes to infinity, means the new it becomes e power 0, that means 1. So 1 minus 1, this term entirely vanishes, and your end to end distance becomes equal to your uh, contour length. Contour length is nothing but when you stretch the polymer chain, you take a single polymer molecule and then stretch it completely, that end to end distance is your contour length. Whereas your persistent length, it is dependent on your uh, uh, it is not your entire contour length, but it depends on how it can be, how your flexible or rigid your polymer is. Okay, and how you can correlate, the different segments, how uh, the the position of different segments. For example, if you just take this kind of a polymer coil, how can you correlate the first point and the last point? So that depends on the persistent length. Okay,
Okay.
when you are able to correlate that better, that means your persistent length is more, that means the polymer is more rigid. Okay, because for example, if you
Okay.
just take this length, these 2 points, you can correlate it. If this point is here, obviously your this point will be here, you can correlate, right? It will form on the straight line, you can correlate, you can develop some correlation, correct? uh,
Okay.
how the orientation will be. Whereas for this more of a coiled structure, it's very difficult. This point is here, but this point is somewhere here. You cannot correlate. Maybe in the next moment, it may be somewhere else, right? Depend if it is able to bend much more. Here, your bending capability is very less, so it will be much more of a expanded chain. Whereas in much more coiled chain, your bending capability is much lower. Sorry,
Okay.
in a coiled chain, the bending capability is much higher. So you cannot really correlate. So it gives an idea of, the correlation between the different points in the polymer chain based on its capability
Okay.
to bend and its flexibility. It gives an idea of flexibility and rigidity of a polymer chain.
Okay. Understood.
Okay.
Understood, ma'am. Got
Yeah.
it.
But contour length is just, just stretch open the chain from one end to the other end. What is the length? That is what is the contour length.
Yeah, I misunderstood contour length for persistent length.
Yeah. Okay. Now, sorry, let's get on to the session. Any other doubts?
No, ma'am. That's all.
Okay. Yeah. Now let's get on to the practice assignment session. Flexible PVC tubes are used for watering. Okay, if some organic solvents are passed through this tube, it becomes stiff. This is due to the fact that the organic solvent plasticize PVC and raise the TG, remove the plasticizer and raise the TG, remove the plasticizer and lower the TG, or react with PVC and increases the TG. So,
React with PVC and increase TG.
does it react with PVC and increase TG? That is why the PVC tubes, becomes much more stiffer.
The molecular arrangement changes.
Yeah, there is a arrangement change. Yes, it becomes stiff. But what happens? What is happening there? Is there is an increase in TG?
Yes, ma'am. Then only it will become a glassy state.
Okay, now let's see the answer. It actually removes the plasticizer and raise the TG. Okay, so PVC, uh, their TG is in general higher, but when plasticizers are added, it becomes flexible. That is where, because in earlier times and all, no, for these pipelines and all, they generally use PVC. Those used to be stiff, if you have seen in buildings and all. Correct?
Yes, ma'am. Yeah,
Yeah,
for plumbing work.
but when you're using it for, watering the garden and all, no, there will be some tubes which are again made of PVC. Those are flexible. So to make it flexible, uh, you know, they add some plasticizer. In fact, in one of the earlier lectures, it was discussed, because of the presence of the polar group, your PVC, they have higher TG, if I'm not wrong. I think there was a
I,
discussion. So, plasticizer will be there in the PVC tubes to make it flexible. So, and that is used for passing water. So, in place of water, if you start passing through organic solvents, what these organic solvents will do is that they can take up these this plasticizer obviously will be smaller molecules compared to the PVC polymer chain. So those molecules will start getting leached out. Okay, and because of the removal of plasticizer, the TG is raised and it becomes stiff. Okay.
yes, ma'am. Got it.
Okay, fine. Next. The correct statement with respect to electrical property of polymeric materials is, for non-polar materials, dielectric constant is independent of frequency and temperature. For polar materials, dielectric constant depends on frequency but not on temperature. For non-polar materials, power losses are high and depends on temperature and frequency. And for polar materials, power losses are low and independent of frequency. Which of these are right?
Option C, ma'am. Power losses are high and depend on
For
temperature and
non-polar
frequency.
for non-polar materials, you're saying. That is right with respect to electrical property.
Yes, ma'am.
Is it? The actual answer is, for non-polar materials, the dielectric constant is independent of frequency and temperature. Because non-polar materials, they cannot polarize, right? They don't have, dipoles to orient. So there will be only some residual polarization. So their dielectric constant is independent of frequency and temperature. It does not change because the material cannot polarize at all, except some impurities or something. They can give some residual dielectric constant. Okay.
So, ma'am, for polar materials, it depends on frequency and temperature, right?
Yes, for polar materials it depends on frequency and temperature,
Okay.
because
Okay.
uh, you know it can the dipoles can orient, okay, depending on the frequency and temperature.
Okay.
Okay, and the dielectric constant is dependent on these two aspects.
Okay.
Okay. Yeah.
Got it.
Yeah. Okay. Now let's go to the next question. The tensile modulus of a thermosetting polyester resin and glass fiber are 3 gigapascal and 80 gigapascal respectively. If a tensile stress of 110 megapascal is applied along the fiber direction on a continuous uniaxially aligned glass fiber reinforced thermosetting polyester composite with a fiber content of 60% by volume, the resulting strain will be dash into 10 power minus 3. This is the GATE 2022 question. So what they have given us, they have given tensile modulus of polyester resin and glass fiber. Okay, and they are saying a tensile stress is applied along the fiber direction. Okay, and additional information they have given is that these fibers are uniaxially aligned. Uh, okay, and they have also given the fiber content by volume. And what is asked is, what is the resulting strain? So how should we proceed with this problem?
Ma'am, we will calculate the total modulus for the composite.
Okay. Anything else we have to take into consideration?
Yes, ma'am. The series or parallel arrangement,
Yeah. Now, what is it you are supposed to do?
but it is not given in the question.
But there are some hints given, right? Identify those hints at least. There are few informations given which we are supposed to take into consideration while solving this problem. See, basic information like individual modulus is given, volume fraction is given, and what is the stress applied is given and all. Okay, but there are some additional information which we have to take into consideration while solving this problem for taking whether it is going to be a series combination or a parallel combination. What is it that is given?
So, ma'am, this will be then parallel arrangement because it's uniaxially arranged in the same direction.
So yes, so the two information which we have to take here are, one is the fibers are uniaxially arranged. Second point is that the stress is applied in the fiber direction. Okay, so as we said, tensile modulus of the resin is given, fiber is given, volume fraction of fiber, volume percent of fiber is given, so volume fraction can be taken, and then tensile stress along the fiber is given. So this is how the system will be, right? So the fiber alignment is in this direction, and the same direction the stress is applied. The tensile stress is applied. Okay, that means the total strain will be same, and the stress taken up by the matrix and the fiber are different. Okay, so the stress taken, so the extension, since the fibers are aligned in one direction and the stress is applied in that same direction, so what is it we have to take into account is that the total extension will be same. That is the fiber extending, for example, it extends from 1 meter to 2 meters, means the matrix will also extend from 1 meter to 2 meter. That means the load taken up by fiber will be different and the matrix will be different, right? Because their modulus are different, so the capability to share the load will be different, right? So this is what you have to take into consideration, and then you have to take your total composite modulus will be your matrix modulus into volume fraction of matrix plus fiber modulus into volume fraction of fiber. Now can you say what will be the composite modulus? Can you calculate and say?
It will be point 3 times 0.4 plus 80 times 0.6.
Okay, so what is the value?
49.2.
Okay, let's see. Yeah, 49.2 gigapascal. So 49.2 into 10 power 3 megapascal. Can you say why I have converted this to megapascal?
Because the question is given in 10 to the power 3.
Is it because of that? Now, what are we supposed to
The,
find?
the tensile stress is given in megapascal.
Yes, yes. So your stress is given in megapascal. So that is the reason I just converted the modulus also to megapascal so that there is a consistency and you can find out the strain directly. Now, what is the strain?
Modulus by stress.
Is it modulus by stress? Is it modulus by stress or stress by modulus? What is Hooke's law?
Stress is proportional to strain.
Okay. So if you remove the proportion and make it as equal to, then you will have a proportionality constant. Correct. So what is the proportionality constant? Modulus. Correct. So now
Oh,
your stress is equal to modulus into strain. So your strain will be,
stress by modulus.
yeah, calculate and say what will be the total strain.
Point 0.23 meter.
Does it have a unit?
It's a strain hormones.
Strain, does it
Should
have
have.
unit?
Yes, ma'am. The distance.
Have they given any unit in the question?
Here, oh no, ma'am. It's not given.
It's actually a ratio. It's ratio change in length to the original, change in dimension to the original dimension. So it doesn't have units because in a numerator, for example, if it is in meter, denominator will also be in meter. So both gets cancelled. So it is a non-dimensional unit. So non-dimensional, parameter. Okay. So your strain will be sigma by EC. So sigma they have given 110 and EC you have calculated 49.2 into 10 power 3 megapascal. So you will end up with 2.2 into 10 power minus 3 as a strain value. Okay.
I got it.
Next. This question is also a very similar question. In a unidirectional carbon fiber vinyl ester composite, the ratio of moduli of carbon fiber to the vinyl ester is 35 and the fiber takes up 50% of cross section. The percentage of force taken up by the fibers is dash percent. Now, how do you solve this?
No idea, ma'am.
It's very similar to the previous question. Okay. So here again, they've given unidirectional. So the fibers are aligned in only one direction. Okay. And then they've given the ratio of moduli. Right. So can we find out what is the, you know, individual material and the composites moduli?
Yeah, I didn't get to, ma'am.
Now, can we find the composites moduli from what is given?
Yes, we can add, but only the ratio is given.
Okay. And what else is given?
The volume fraction,
Yes. Okay.
50%
Yes.
of
Yes.
cross section.
Yes. Now let's see how to solve the problem. So given the ratio of moduli of carbon fiber to the vinyl ester is 35 is to 1. and then volume percent of the fiber is given. They've not given directly as volume percent, but they've given as fiber takes up 50% of cross section. So that means volume percent of fiber is 50%. So volume fraction is 0.5 for fiber and 0.5 for the polymer. Assuming now, here again we are assuming that equal strains for both carbon fiber and vinyl ester. So we are assuming the same combination, right? That the fiber and the resin are extended to the same level, right? That means the load taken up by each will differ, and that is what they have asked. That is what is the hint. The force taken up by the fibers is dash. That is what they have asked. What is the force taken up by the fiber? Okay. So again you have, so your total total stress will be summation of individual stresses, right? So stress taken up by carbon fiber and stress taken up by the ester. So your strain is constant, right? So you are just uh, expressing these in terms of the strain. So uh, so if you express that, then it will be epsilon, which is the strain into uh, carbon fibers modulus into volume fraction of carbon fiber plus strain into uh, vinyl ester's modulus and multiplied by vinyl ester's volume fraction. And then you're taking this, since the strain is constant, you're taking the strain out and you arrive at this kind of an expression. Okay. Now, what I have done is that they've asked the percentage of force taken up by the fibers, right? So percentage of force taken up by the fibers in percentages. For calculating that, what I have done is that first I have taken the ratio of the carbon fiber stress to the total stress is okay. So which is equal to, again you are expressing it in terms of the strain and whatever known parameters, strain and your modulus. So it will be epsilon into ECF into phi CF divided by epsilon overall epsilon multiplied by ECF phi CF plus EVE modulus of vinyl ester into volume fraction of vinyl ester. So you have your relation between your this one strain you do not know. So strain you can just take it as x. Okay, some strain as x, some x strain, and then ECF is 35 into 0.5 because the ratio is 35 is to 1. So you're just assuming 35 gigapascal is to 1 gigapascal. Okay, so divided by 35x into 0.5 plus 1x into 0.5. Okay, if you just substitute, so xx cancels out both place in both the places. Okay, and then finally you arrive at 0.972, which is 97.2 percentage of force is taken up by the fiber. Okay, individual stress by total stress will give you what is the percentage of force taken up by the fibers. Right, to calculate the percentage individual by total, 35 percentage means 35 by 100, right? The same thing we are doing it here. You got it?
Okay. Yes, ma'am.
Okay,
Got it.
okay, fine. It's just playing with mathematics. That's it. End of the day, you have to take that the strain is constant, or both the fibers and the uh, polymer extend to the same level. Okay, and then you have to proceed with the further calculations. Next, solubility parameter of polystyrene is 9.1 calories per centimeter cube whole power half. The solubility parameter of N-hexane is 7.3 calories per centimeter cube whole power half, and that of benzene is 9.2 calories per centimeter cube whole power half. Then polystyrene will it dissolve in N-hexane or not dissolve in 80:20 mixture of N-hexane and benzene, or not dissolve in benzene or dissolve in benzene. What will happen? This is a GATE 2011 question. They have given solubility parameter of polystyrene. They have also given solubility parameter of N-hexane and that of benzene. Now they've given certain statement and they've asked what will be the case with polystyrene. Will polystyrene dissolve in hexane, or will it not dissolve in benzene, or will it not dissolve in hexane and benzene, or will it dissolve in benzene?
Option D, ma'am. Dissolve in benzene.
Why do you say so?
The solubility parameter is higher than polystyrene.
Is it that way? Your answer is right. It dissolves in benzene, but the reason is that polystyrene and benzene, they have very close solubility parameter. Okay, whereas in hexane it has a little different solubility parameter. So the closer the parameters, then their interactions will be much better, and that is why polystyrene can be dissolved in benzene. Okay.
Okay.
Okay. So in when you had gone through the lecture, they would have shown that uh, the cellulose, the water solubility parameter and the cellulose solubility parameter will be a little closer. But there would have been a discussion that cellulose does not dissolve in water,
Ah,
right?
yes, ma'am. There was a
Yeah.
discussion, yes.
Yeah.
And in
Why
organic solvents, also it's not soluble
soluble? Why was it?
because of the hydrogen bonding.
Yes, it has,
And
a very high level of hydrogen bonding, so it makes it not soluble in any of these kind of solvents. So it is not just the solubility parameter, but there are much more, parameters that are to be considered to see if a material is soluble in particular solvent. Solubility, parameter gives a rough estimate. Okay.
okay, got it.
Yeah. Next, chemical aging by photooxidation leads to conversion of C double bond C bond in natural rubber to dash bond, whether it is CHCH or COH or COOH or C double bond O bond.
Ma'am, carbonyl bond, the C double bond.
Yes, you are right. So when photooxidation or ozonolysis happens, you form a C double bond O and C double bond O. I mean, you end up in a ketone and a aldehyde. So carbonyl compound is formed. All right. Next, for a polymer which follows the Markov equation, the various parameters determined were as follows: K is equal to 1.2 into 10 power minus 4, eta is equal to 2.4, A is equal to 0.76, and Huggins constant is 0.33. Concentration is 0.3 gram per deciliter. Okay. Now, what is the molecular weight of the polymer? Is it 4.5 into 10 power 5, or is it 6.1 into 10 power 4, or is it 3.2 into 10 power 6, or is it 7.9 into 10 power 5? So, how do you find?
And from the Markov equation,
Okay, what
the
is.
e-
Hmm,
eta equal to K times m to the power of constant.
okay, okay, that's good. So, find out and say what is the value of the molecular weight of this polymer.
Ma'am, I got molecular weight as 4.5 into 10 raised to 5.
Okay, now let's see. Uh, yes, you are right. So your Markov equation is eta intrinsic viscosity is equal to K into m power A. So substituting, we have all other parameters except for molecular weight. So if you substitute, you will end up with the molecular weight as 4.5 into 10 power 5. Now tell me one more thing. Is this particular solvent, okay, uh, in which this polymer is present, is it a good solvent, or is it a theta solvent, or is it a bad solvent?
Ma'am, it will be uh, good solvent because concentration is very low.
So based on concentration, there is another parameter which you have to actually look into to say whether it is a good solvent or a ideal solvent or a bad solvent. There is one more parameter. There is a parameter, different parameter you have to look in and see. It's actually your A. A will say, the power exponent will say whether it is a good solvent or a ideal solvent or a bad solvent. Okay. So, because this A, you can correlate the molecular weight to your radius of gyration. And from there, you can get the constant. By correlation, you can get that for an ideal solvent, A will be around 0.5, and for a good solvent A will be around 0.8. Okay, so here A is 0.76, which is very close to 0.8. Okay, that means it is a
A good
good
solvent.
solvent. Good solvent. Yeah, this is discussed in that lecture. You just go through, and in fact, there was a question asked in week 3 assignment, I guess week 3 or week 4, if I'm not wrong. What will if the exponent value is 0.5, whether what kind of or exponent value is low, whether it will be a good, what will be the chain conformation of the uh, polymer, whether it will be ideal chain or something, and the answer was ideal chain. Just go through that question also. Okay.
Okay, ma'am.
Yeah. Next is, they've asked one more part: what is the specific viscosity of the polymer, of the above polymer? Okay, to find out that, they've given a Huggins constant 0.33. Okay, now you can find out specific viscosity uh, by the Huggins equation, where the Huggins equation gives specific viscosity by concentration is equal to intrinsic viscosity plus Huggins constant into square of intrinsic viscosity into concentration. Okay, this basically gives this how much, what will be the specific viscosity depending on the concentration of the polymer, right? So here we already have what is the concentration. They've given us 0.3 gram per deciliter. We also have Huggins constant. We also have intrinsic viscosity value. Now, can you find out what is the specific viscosity? Whether it is 0.73 or 1.12, or is it 0.89 or 2.3?
Ma'am, is eta SP the specific viscosity?
Yes, eta Sp is the specific viscosity, which is related to the polymer viscosity and solvent viscosity, as this. Okay, it is eta minus eta S by eta S, where eta is your solvent viscosity and eta is your polymer viscosity.
Ma'am, it's 2.4.
Okay, you're getting 2.4. Let's see how it is. It's actually 0.89. So you have your intrinsic viscosity 2.4. So here your concentration is in the denominator. If you just cross multiply, you will have in both the terms, there will be a concentration term multiplied. So eta into 0.3, sorry, eta into concentration, and this term also multiplied by concentration. So here it will be concentration square. So it is 2.4 into 0.3 plus 0.33 into 2.4 square into 0.3 square. So if you do the multiplication, you will get a specific viscosity is 0.89. Okay.
Yeah.
Okay. So electrical conductivity of doped polyaniline is dash Siemens per meter. Is it 10 power 7 or is it 10 power 14 to 10 power 16 or 10 power minus 14 to 10 power minus 16 or is it 10 power minus 2 to 10 power 4?
It would be around in the semiconductor region, 10 raised to minus 2 to 10 raised to 4.
Yes, you're perfect. That is 10 power minus 2 to 10 power 4, which is the semiconductor region. Next. In complex conductivity, the real part of complex conductivity represents dash of energy, while imaginary part represents dash of energy, which represents storage and which represents dissipation of energy in complex conductivity.
Uh, uh, Real part is storage and imaginary part is dissipation.
Is
But
it?
I'm not sure, ma'am.
Okay. It's actually real part is dissipation and imaginary part is storage. Because in conductivity, the real part is, it represents the conductivity, that is the flow of charges, right? So there is a flow or movement, right? That means there is a dissipation of energy. Okay. Whereas your imaginary part, it represents your storage of energy. That means there is some polar dipole orientation. It is in a way kind of a storage of energy, storage of electrical energy. Whereas your real part, it actually represents, since it is conductive, the real part represents the flow of electrons or flow of charged ions or whatever it is. So it is actually dissipation of when there is a flow. For example, in mechanical terms, your real part represents your energy storage and your elastic part, and your dissipation represents viscous part. Viscous means there is a flow or movement of or there is a segmental mobility or molecular mobility, right? So here also there is a charge mobility. That is why it represents dissipation of energy. Whenever there is a flow or there is a movement, there is a dissipation associated. Okay,
Okay, ma'am.
you got it. You
Yeah.
have to just correlate that mechanical to your
Mm.
electrical also. So there is a flow of charged component, so there is a dissipation. Okay, next.
Yeah.
Identify the response variable from the following: stress, refractive index, strain, current, permittivity, light, viscosity, which are all response variables. This was discussed in the lecture when there was a discussion on linear response. So there was a discussion on input variables, output variables, and response variables.
For stress and strain, it is modulus.
No, you just have to identify which are all the response variables in general from the
Like,
given set.
okay.
There are 7 parameters given, which are all the response variable from the given 7 parameters. Is stress a response variable? Is refractive index a response variable?
Refractive index,
Okay.
permittivity, and viscosity.
Okay. Let's see. You are right. A refractive index, permittivity, and viscosity are the response variables. So stress, strain, current, and all they are all input or output variables. They can be either input or they can be either output. Okay. Next, scaled response and superposition are features of dash response.
And the linear,
Yes.
linear.
Yes. Linear response. In linear response, actually, for example, you have the resistance data of particular electrical system for a particular voltage applied, and then when you double the voltage, then the corresponding scaling can be done, okay, to the response, okay, uh, or superposition can be done. For example, one set of voltage you're applying and then another set of voltage applying, what will be the sum? If you apply, for example, 1 volt you're applying, 2 volt you're applying, so when you're applying 3 volts, what will be the response? So you can just add the response of 1 and 2 volts and get will be the response of the third 3 volts application. Okay. So significant changes in material structure is a feature of dash response. What kind of
Uh,
response?
I don't know.
You said something to the previous one, a different one from
Yeah,
that.
and non-linear.
Yes. In nonlinear response, there will be a significant changes in the material structure because there will be some, orientation and alignment and structural, significant structural changes that is happening. Whereas in linear response, there is a very small, minor effects that is happening. That is just small movement from one equilibrium position to another equilibrium position, depending on the stimulus. And once the stimulus is removed, it comes back to the original. That is what is linear. Whereas in case of non-linear, it is not the case. There is a significant material or structural changes that is happening. Sorry, not material. It is a significant structural changes that is happening to the material. Okay. So these are the answers. Now next, match the processes with the response of the material. Atomic polarization associated with vibratory modes of atom, molecular relaxation associated with translation, rotation, and vibratory modes of bonds or molecules, electronic polarization associated with electronic relaxation process. So the responses are conducting response, optical response, mechanical and dielectric response. Which of these corresponds to which type of relaxation or which type of processes?
Yeah, these all are electromagnetic response.
No, you have to match ABC with 1, 2, 3.
Atomic polarization with mechanical and dielectric. Uh,
Okay.
molecular with conducting response, and electronic with optical.
Is it?
Yeah,
Okay, now let's see the answer. It is actually atomic polarization, which is associated with vibratory modes of atom. It gives you the optical response. Molecular relaxation process. Okay, molecular scale process that is happening only. It gives mechanical and dielectric response. Okay, which is associated with translation, rotation, and vibratory modes of bonds or molecules. Right? And finally, electronic polarization is that is associated with electronic relaxation. It gives the conducting response. Fine.
Oh, okay.
Next is macromolecular orientation and creation of polymer microfibers surrounded by voids leading to whitening of sample is it called shear banding, or is it called cold drawing, or is it necking or crazing?
Um, Option B, cold drawing.
Cold drawing, you're saying. Is it so? It's actually crazing. In crazing, what happens is that there is a macromolecular orientation. So this, because of this orientation that is happening, the polymer, the orientation will be in the shear direction or in the force application direction, and there will be polymer microfibers kind of formation. Okay. And since there is a concentration of polymer microfibers in one part, there will be a void in the other part. This leads to a process called as crazing, and it leads to whitening of sample, and this is actually called as a crazing. Okay. Cold drawing is the nothing but your there was also a question in one of the previous assignments, right? For one of the material, you cannot do cold drawing because in room temperature, you cannot stretch the material because the material is below its glass transition temperature, and it's tough to pull the material and stretch the material. So cold drawing is basically stretching of the material under cold condition. Okay. But here in crazing, what is where you have the orientation and formation of microfibers, and voids formation is also there, which leads to whitening of sample. Yeah, because there is a concentration in one point, and there is a void in another point. So this leads to the light, when light passes through, there is a difference in refractive indexes, because the point where fiber is present, it refracts more, whereas where there is a void, there is a less refraction. So this leads to the appearance to be white because of the difference in refractive index between one point and the other point. Okay. Are you
Okay,
able to
ma'am.
follow? Yeah.
Yeah.
Okay. Okay. Next, plasticity model based on concept of energy barrier for conformational changes. Which model? There were two models discussed, right? For plasticity.
Yeah,
Uh,
one was a ring model and
yeah.
the
What was it?
second one I don't remember.
Right. So these are the two models: Eyring model and Ramberg Osgood model. So which of these is based on activation energy barrier concept?
The first one, a iron model.
Eyring model. Okay. Let's see if you are right. You're right. Eyring model is actually based on energy barrier. Okay. Uh, so it has this activation energy kind of relation. Okay. Whereas your Ramberg Osgood model, it is based on the power law relation. Okay. There is a linear term plus there is a power law term of stress to modulus. Okay. So that
Yeah.
is what. Next. The volume resistivity of a polymeric material is 10 power 7 ohm meter. Find the resistance in mega ohms of a cube of a material of side 1 centimeter. The direction of current flow is as shown in figure below. This is the current flow direction. Now you have to find out the resistance. It's a GATE 2014 question. How do you proceed? They have given resistivity and they have given the side of the cube is 1 centimeter. They have asked for resistance. How do you find? This is very simple question.
There is one direct formula, but I forgot it.
Okay. You forgot the formula, but that's okay. But what are the terms you have to consider here?
Resistivity, uh, length, and area of cross section.
Yes. Yes. Your volume resistivity is given as rho is equal to 10 power 7 ohm meter. So they have asked for resistance given cube of material with side 1 centimeter, that is nothing but 0.01 meter. So resistance is rho L by A. So length is 0.01 and area of cross section is 0.01 into 0.01 because it's a cube. So if you just multiply by length and divide by area of cross section, the resistivity multiplied by length and divided by area of cross section, you will get 10 power 9 ohms, which is nothing but 1000 mega ohms. That is the resistance of the material. Okay. Now next, based on the solubility parameter, the best solvent for polyethylene uh, will be the solubility of solubility parameter for polyethylene is 16.2 megapascal power half. And then they have given 4 solvents. One is tetrahydrofuran, the solubility of 20.3 megapascal power half. Toluene, solubility parameter is 18.3 megapascal power half. Acetone, solubility parameter is 19.9 megapascal power half. And methanol, uh, the solubility parameter is 29.7 megapascal power half, which will be the best solvent.
Toluene. To-
Why do you say so?
it was discussed in the earlier question, the nearer value.
Yes, you are right. So toluene, which is having 18.3 as a solubility parameter, is closest to that of polyethylene, so which is 16.2. So that is the best solvent for polyethylene. Okay, next. Identify the physical aging process in polymer among the following: crystallization, oxidation, phase separation, cross-linking, chain scission.
Uh, Oxidation, phase separation, cross-linking, and chain scission.
All these four are physical aging, is it?
Crystallization.
All five are physical aging process, is it? Identify the physical aging process.
Oh, physical. So it will be crystallization, phase separation, and cross-linking.
Okay. It's actually crystallization and phase separation only. Those two are only physical processes. Whereas oxidation, there is a chemical reaction happening with oxygen. Cross-linking also with some material, there is a chemical reaction that is happening. Chain scission, there is a breakage of chain. So there is a bond breakage. So that also involves a chemical reaction. That is a bond this breaking. The other two bond forms, here the bond breaks. So all the other three are chemical aging process. Only crystallization and phase separation are physical aging process. There is no reaction or anything involved. Okay. Now next, persistent length of polyethylene is 0.7 nanometer, while that of double stranded DNA is 30 to 80 nanometer. This implies that polyethylene is dash than double stranded DNA. So we just had a discussion on persistent length, contour length, right?
Ah, yes, ma'am.
Now tell me,
Polyethylene is stiffer than double standard DNA.
It's stiffer than double-stranded DNA.
Because persistent length is small for polyethylene.
If it is small, so can we correlate one end, the if we know the position of one end, can we correlate the position of the other end of polyethylene chain for this persistent length?
I don't know.
Just now we had a discussion.
No man, no idea.
Polyethylene is more flexible. If the persistent length is small, no, the rigidity is small. So you have small units, right? So it will be much more flexible. Okay, if the persistent length is of the contour length order, that means it is a more, rigid chain. It is not able to bend or anything, right? So till 80 nanometer, it cannot bend, right? It is stiff portion. It's kind of some rods. So that means it is not bendable. So it's much more of a, you know, a rigid chain. That means you can correlate those chains, one position to the other position easily. That is what we saw. So it has an exponential correlation, right? So when the persistent length is small, your correlation, it falls off. When LPS tends to 0, this is an exponential relation for correlation. When LPS tends to 0, when persistent length is very small, so here it is very small, like, I mean, 0.7. So so here it approximately becomes 0. So exponential of 1 by 0 is exponential of minus infinity, right? 1 by 0, exponential of minus 1 by 0 is exponential of minus infinity, which is nothing but 0. That means you cannot correlate where the other will be. That means it is very flexible, that it moves like anything, that you cannot correlate how the position of the other end of the chain will be. Whereas if this value is very high value, then it will be more of an extended straight chain. So one point to the other point can be easily correlated, right? So if this persistent length is large, so say for example, if the persistent length is infinity, 1 by infinity, that means it is 0. So correlation is 1. That is what you have, a very perfect correlation. You can say where the other end of the chain will be there when you know the one end of the chain, if it is here. Now you got it.
Yeah,
You're clear now. So
yeah,
yeah, perfect, perfectly clear, right? That means it says,
yeah,
how flexible the chain is. The persistent length is small, very small. That means the chain can bend and, flex. Whereas the persistent length is large, uh, you know, it is of more of a rigid zones, right? Persistent length is nothing but it is the persistence of the correlation between one end of the chain to the other end of the chain. Okay. If the higher the persistent length, then easier is the correlation. If the lower the persistent length, the correlation is very less. Okay. Now
yeah,
hope you are clearer than earlier. And if the persistent length, is very high, of the order of contour length, so the chain is much more rigid. Okay, it's like a kind of very extended open chain. Sorry, it's more of an extended conformation, because it's very rigid. It cannot fold or coil. Okay. Hope you got it.
yeah.
Okay, fine. Next, dielectric permittivity can be obtained from dash component of the electric field and electric displacement.
No idea.
Whether it is in phase or out of phase.
In phase.
Dielectric permittivity. Uh, if electric field and electric displacement are in phase, you can find the dielectric permittivity. Okay. So if electric displacement and electric field are out of phase, you can find the uh, conducting or the dielectric loss. Okay, conductivity or the dielectric loss. In other words, if current and voltage are out of phase, you can find out the dielectric permittivity, and if current and voltage are in phase, you can find the dielectric loss. Okay. Now next, examples of practical phenomena of nonlinear response includes. Where do we find nonlinear response in practical applications?
In yielding.
Okay.
Then then I don't know.
So yielding, fracture, electrical breakdown. Right, in fracture, there is a significant structural change. The material is fractured, right? The bonds are completely broken and the material is fractured. So these are all, responses that come under the nonlinear response. Okay, examples of response that come under nonlinear response. And there's a significant structural change. Next. Dipole in PVC is on the dash, while in PEO, it is along the dash. In polyvinyl chloride, where is the dipole? And polyethylene oxide, where is the dipole?
In PVC, it is on the side chain.
Okay.
In PEO, I don't.
In PVC, as you said, it is on the side chain, CCl. This is on the side group. Okay. Whereas in PEO, it is on the backbone because CH2 and O. So C and O, these form the, these two form the the group that can have the dipole orientation. Okay, it is along the backbone. Next, in Debye relaxation model, when frequency tends to 0, then dielectric permittivity tends to dash, and um, your dielectric loss is proportional to dash. At very low frequency, what happens to permittivity and what happens to dielectric loss? In Debye
Uh,
relaxation.
the permittivity will be maximum.
Okay. What about the dielectric loss? Will it be proportional to frequency or will it be inversely proportional to frequency?
Then it will be a proportion.
See, as you said. So when omega tends to 0, your dielectric permittivity will be maximum, which is ES, epsilon S, and when your dielectric loss will be proportional to frequency. So this is how it is. So when omega tends to uh, 0, so here in E prime, epsilon prime, your in the denominator, your omega is 0. So your omega goes off, and epsilon infinity plus epsilon s minus epsilon infinity, you will get epsilon s as the uh, dominant polarization as the value. And what happens in case of your epsilon double prime? When your omega tends to 0, again here in the denominator, omega square, it's already 0, it's a very small value, so it's 0. So here again it goes off, so you will have your dielectric loss is proportional to omega. Okay. So this is what is the explanation. Okay. So
Yeah.
next. When a woven fabric is reinforced in the polymer, the properties are similar along the plane, while different along the thickness direction. And this nature is referred to as
No, no.
called as transversely isotropic. So in the transverse direction, there is a uniformity in the property because it's a woven fabric, two-dimensional fabric. So the properties in this along the plane will be same, but along the thickness direction, it will be different because it is more of a polymer-polymer interaction than the interaction with the fiber. Whereas in the transverse direction, there will be a polymer and fiber which is taking up the load. Okay, so that is why it is transversely isotropic. The properties will be same in the transverse direction. That is why it is transversely isotropic. Whereas in the thickness direction, it will be a different. Okay, you got
Yeah.
it? Yeah.
Yeah.
Okay. Dash of reinforcement or fillers leads to orders of magnitude increase in properties. The filler amount should
It should increase.
reach certain parameter. What is that term called?
Idea.
It's called as percolation. Okay. So when it reaches the percolation, so what happens is that as you keep on increasing the filler concentration, there will be a point where the fillers start getting connected. Okay, and you can see the magnitude increases in multiple orders. For example, your electrical conductivity may increase like multiple folds from insulating to a semiconducting or conducting region it will touch. Okay, so percolation has to reach. Fine. Next, yielding leads to processes which dash the energy, leading to permanent deformation.
Dissipation of energy.
Yes. So there is a dissipation of energy. So since there is a loss of permanent loss of some energy, there is a permanent deformation. It cannot. There's no energy for the material to come back to its original state. Okay. D by relaxation on a cold plot is, what is the shape of the plot?
No idea.
It is a semicircle. So when you plot your dielectric loss versus dielectric permittivity, you will get semicircles. And for real materials, you will get multiple semicircles. That means it is nothing but there are multiple relaxation processes involved because of the complexity in the polymeric structure. Okay, that's it with the session. And actually, this was asked in one of the earlier forums. So they asked how to solve this problems which was asked in assignment 5. So if a rubber cuboid sample is stretched to its original length along one direction, the cross-sectional area will be dash its original cross-sectional area. So whether it will be half or twice or same or 1 by 1.4 times. So you have the
Will
length
be
become,
half.
yes, it becomes half because your length becomes twice. So L by L naught is 2. That is your stretch ratio is Q. So incompressible rubber. So uh, initial dimensions is equal to the volume initial is equal to the volume final because the rubber is you are assuming incompressible rubber. So L naught B naught W naught is equal to LBW. So that means your lambda SRX, SRY and SRZ multiplication is equal to 1. So, and then you will get, so lambda SRX is L by L naught, SRY is B by B naught, and SRZ is W by W naught. So this is what is the figure. So, 2 into lambda SRY into lambda SRZ, that is equal to 1. So that means it is equal to half. Your cross-sectional area will be half of the original cross-sectional area. And then there was one more problem, question number 12, where the tensile force of 250 Newton is applied to a cuboid rubber sample of length 30 mm. Cross-sectional area is given as 5 into 5 mm square. If the length of the sample is elongated to 150% of original length, under the same applied force, the true stress will be, what will be the true stress in Newton per millimeter square, they have asked. So here again, your tensile force is 250 Newton, and then your length of cuboid is 30 millimeter. Area of cross section is 5 into 5, that is 25 mm square. So length, it is elongated by 150%, that means 1.5 times of the original length. So lambda SRX is 1.5. So again, your cross sectional area will be 1 by 1.5, correct? Because again you are using the incompressible rubber. So your new cross section will be 1 by 1.5 times the original cross section, that you will end up with 16.67 millimeter square. So true stress is applied load by actual cross sectional area. So your applied load is 250 Newton and your actual cross sectional area, which is the new cross sectional area, is 16.67. So you will end up with true stress as 15 Newton per millimeter square. Whereas if it is asked, if engineering stress is asked, then it is applied load by original cross sectional area. This 250 by 25, right? You will end up with 10 Newton per millimeter square. Okay, that's it.
What is the difference between true and engineering stress?
That's what, this is the formula for in your true stress takes the actual cross sectional area, because since you're considering the system to be incompressible, the volume remains constant. That means if there is an increase in length, there will be a decrease in cross sectional area. So when you are accounting for true stress, you have to account for the changed cross sectional area, which is the decreased cross sectional area, right? The cross sectional area has decreased from 25 to 16.67. So you have to consider that 16.67 as the cross sectional area for estimating the true stress. Whereas in engineering stress, you have to consider only the original cross sectional area, not the changed one. Okay.
Okay.
So that's it with the session. Any other doubts?
No, ma'am. That's all.
Okay. So you are now clear with the persistent length concept?
Yes, ma'am. Yeah, clear.
Yeah. So if persistent length is smaller, then the
It will
polymer
be
chain.
flexible.
Okay. Okay. If there's a, so can we correlate the orientation of one end to other end easily? If the persistent length is
Uh,
small.
No, ma'am.
Okay. No. Yeah.
Now it's
Yes.
clear.
Okay. Fine. Good. So that's it with the session. So if there are no more doubts, then we can officially end the session.
Yeah, thank you very much, ma'am.
Yeah. Thank you.